The title is Addressing the Validation Problem for Social Simulations, and I should add the game theoretic models. And one extra bit of information is that it's about a particular approach that I've been developing called the adversarial scheduling approach. And as far as I'm concerned, evolutionary game theory and mathematical models in that area and agent-based social simulation, or social simulation for the matter, are just two sides of the same coin. You can see here a very typical phase diagram picture from evolutionary game theory versus a sugarscape model. In particular, a lot of the models, basic models that the two simulations, the two areas deal with, are very similar. And I'm going to be concerned with a class of models, interaction-based models developed by Blum and Durlov. And basically, we have a bunch of agents located at the vertices of a graph or hypergraph. Each agent has a state. And what they do is then, when scheduled, an agent updates its state as a result of interaction with its neighbors in the hypergraph. Usually this interaction is based on game theoretical mechanisms, like I play a game against a random neighbor or against every of my neighbors. So there are many versions of this type of game. And how do we interpret results, be them mathematical or obtained from social simulations? One possible answer is that we look at particular results, and then we go to stylized facts. And we're looking for mechanism or mechanism-like explanations of social dynamics. I'm not going to say here what the mechanism is. I'm not even the most competent person to do it. I'm a computer scientist, not a social scientist. But as far as I'm concerned, at least part of a definition of a social mechanism would imply a causal connection between features of the simulation process or of the mathematical result. And just to give one concrete example, if we talk about equilibrium selection problem in game theory, one result, an insight due to Peyton-Young, was that adding a little bit of noise to a best response dynamics can choose, in certain cases, one equilibrium out of several equilibria that a game might possess. So here the mechanism is addition of noise, and the addition of noise causes the system to choose one of the equilibrium. So it goes along the causal link that I outlined. Obviously, when we're dealing either with mathematical models or with agent-based simulations, we're dealing with the important problems of verification and validation. In particular, how can we make sure that the results and the conclusions that we obtain are not crucially dependent on some peculiar features that we're adding to the models? This is hardly an academic question. There are massive agent-based models that have been developed in the United States, such as Transims, which is a traffic simulation. The project had a budget of like $25 million, and it's an agent-based simulation of 1.5 million people in a city like Portland, and it was supposed to be deployed in urban planning authorities around the United States. Or in recent work about pandemics and vaccination strategy for epidemics, there are models going from very simple agent-based models with two cities, such as a model by Epstein and others, to, again, versions of Transims that have millions of agents and put a lot of information into it. And it's not clear which of these two models, for instance, is the best. Which one are we using it? It's very important, obviously. We're going to recommend a vaccination strategy based on a result of such a model. And there are lots of factors, obviously, that can influence the validity of a model. A few of them are social network topology, interaction structure, higher order emergence. We have Nigel here in the audience. I'm only concerned in this talk with one, and that's the order in which agents update. Okay? This is a topic that has been studied before previously, and there is a famous paper by Bernardo and Natalie Glantz on the serial versus parallel properties of prisoner's dilemma. but I would like to do something that is a little bit principled. And the interest in this type of approach for me came in the context of looking at mechanism-based explanations. Both in agent-based social simulation and more generally in analytical social sciences, these types of explanations have received some attention lately. In particular, Josh Epstein has put up a generative approach to social sciences to explain a phenomenon, in his words, includes to grow it. And in analytical social sciences, again, Peter Hedstrom has discussed mechanism-based explanations as one of the types of social theory. I have there a box that would represent Epstein's motto there, and it's a tentative notation. I haven't invented it. It comes from discourse representation theory, which is a sub-area of natural language understanding, natural language semantics. And basically it represents a context. And the way we have it, that's basically an implication. And there is a lot of information, contextual information missing in there. And what we want to say is that if that information is true, then eventually property P will hold. And eventually there is not only a word, it could be a quantifier in a temporal logic. So I only wrote it like that because I presume that not many people know temporal logic in this audience. It's only one of the three types of explanation that Hedstrom puts up. The other ones are covering laws and statistical correlation laws. Mechanisms can be concatenated. There is a paper about concatenation of mechanisms in a previous book by Hedstrom and Swedberg. So a clear question is, what is a mechanism? Could we precisely specify what a mechanism is and perhaps maybe automate the process of identification of mechanisms in social simulations? That's what I'm ultimately interested in. And one problem with this approach is that it has to involve some sort of logic. And logic and social sciences are often cats and dogs. A few times when I've seen the usage of logic in social sciences comes from Elster first, some sort of temporal logic. It wasn't very developed. And also in organization theory, that's probably the most advanced application that I know by Gabor Pelli and Michael Hannon. And ultimately, what I would like to do is come up with hints for a logical-like mechanism that would be able to represent mechanisms in social sciences. Now, I'm not going to do that in the context of social simulations here. I'm going to do it in the context of some mathematical results. And what I'm going to do is take a game theoretic model and develop in a bottom-up fashion. I'll start with something very simple, identify mechanisms there, add more features to the model, look at the mechanisms that underlie the properties of the model there, and so forth. And I'm only going to concentrate on one particular feature. That's the order in which agents update. And we've heard this idea of a controlled experiment. As far as I'm concerned, simple mathematical models like the ones that I'm going to describe and their theorems behind it have this remarkable property that they function as controlled experiments. If you want to talk about various agent schedules, you can often reverse engineer the properties that a scheduler need to satisfy from the proof that you could get for that type of result. Okay, so in a certain sense, that's something that's harder to do in real life social simulation. That's why looking at mathematical models, it's a good first step, I think. And as I said, it's a bottom-up approach. A bottom-up approach has been used before in various contexts, from Sugarscape to Brownian agents and the work on varieties of emergence. And what I attempt to is to provide this insight on the ingredients of mechanism-based explanation. And I'm going to start with something that is very trivial. N agents, totally uncoupled. Each agent has a binary choice, or A or B. And each agent has the same utility. And A is better for each agent than B. There could be hardly anything more trivial than this one. There is no social interaction. There is nothing in there. The only thing is that I started with a random scheduler, okay? And the stylized fact, trivial one in this context, is if I randomly schedule agents, eventually the system will converge to every agent choosing the best choice. Okay, so this is a very simple fact that I shouldn't try to explain anymore. And in the types of notations that I had before, I could try to explain something like that. And again, eventually is a temporal quantifier. And the sign there is my temporary notation for causality. So fairness of the scheduler. So if now instead of a random scheduler, I put an arbitrary one, obviously if I'm not ever going to touch you, you're never going to change your state. So in order for the system to converge to the state where everyone has its best choice, the scheduler has to be fair, has to eventually schedule everyone. Okay, very simple stylized fact that we can infer. Now let's take a look at the conclusion there. What are fair of S? S is the scheduler. That's a property of a process. Okay. The same is there is a property of the process in temporal logic. So my logical framework that I would like to put up for simulations has to be able to express properties of processes and to encode processes. Okay. A second, slightly less trivial fact, but still very easy, is the fact that the convergence time for a random scheduler is of the order n log n plus theta of n. This is a standard combinatorial result called the coupon collector lemma, and you can consult any combinatorial text for its proof. And as I said, for an adversarial scheduler is a scheduler that is fair. Second type of result, if we look carefully at that result about the convergence time, what's happening there is the following. We're taking one domain, which is the domain of bins and balls, which is the area in which the framework in which we're stating the result on the coupon collector, and we're projecting that model onto a model where we have agents and time steps. Again, this is very trivial, but there is a projection, and if you know Lakoff's work on mental models and projections, what I'm trying to say is that you have a context there, and we're projecting balls to agents, bins to time steps, and we infer the thing from the properties of the basic context. We infer the second one. So this is a semi-formal way for now of representing this argument, the fact that the coupon collector lemma implies the result about our agents. Okay, let's go to something a little bit less trivial. So instead of having our agents always choose its best state, we're going to make each agent choose its best state with some error, small error at 1 minus epsilon. Now, of course, we no longer can guarantee that the system goes to everyone being A under random scheduling. Instead, what will happen is that most agents will be in state A most of the time. In fact, 1 minus epsilon of the time, and the fraction of agents. So what's happening when we go to adversarial scheduling instead of random? So what I said before was true for random scheduling. What about the adversarial one? Is this stylized fact true if we replace every x in there with at least 1 minus epsilon or something like that? No, it's not true, because we haven't said what a scheduler is, but if a scheduler can act based on the state of an agent, it can forever preclude the system having too many A's. Say, for instance, you have a B, and I schedule you until you still have a B. So I continue to schedule you until you still have a B, and there will be a small probability that that happens at each step. And Eventually that will happen, and then I go to another agent, and I do the same thing, and so forth. And if I look at the fairness properties of this scheduler, and I have to define technically what fair scheduler means, the scheduler has the same fairness as a normal one. Less trivial than that, let's go to a model where we add the interaction, and now we're going to have a weighted network, and we're going to play a binary coordination game, and we're going to assume with two strategies, and we're going to assume that A has a risk-dominant equilibrium. I'm not going to define that right now. And the mechanism will be a smooth version of the best response dynamics with a parameter beta that is dependent on the total payoff that each strategy would give me based on game playing against every of my neighbors, so when scheduled. Okay? And the concept that is important in this result is belongs to Peyton-Young, and the result is about stochastic stability. And I'm going to, in the interest of time, what will happen is the following. When I perturb the dynamics, I will make the Markov chain ergodic. And if a state has positive probability when I turn in the stationary distribution of the perturbed chain, when I turn the volume of noise down, then I will call the state stochastically stable. And Peyton-Young's insight was that for games that have a risk-dominant equilibrium, you have the state all A is the unique stochastically stable equilibrium. I should have said that another Nash equilibrium in that context is that everyone plays B, and there can be other ones. Okay? And he proved that under random scheduling, the state A, where everyone plays A, is the unique stochastically stable state. I'm going to do this result under adversarial scheduling, and a random scheduler is non-adaptive. I don't use the information about the state of an agent to decide whether I will schedule it or not. And I can do the same thing as in my easy case. If I have a adaptive scheduler, I can preclude stability. So I'm going to take a model, a basic model of a non-adaptive scheduler, and I'm going to assume that I will influence, if I was scheduled this time, I will pass my influence to a random person based on another network that is not necessarily the same as a game playing network. So the influence who gets activated makes a random walk on this network. This generalizes the notion of a random scheduler for the case when this network is a complete graph. It is specified as a Markov chain on the state of configurations times the last agent that played. And I proved that under such a scheduler, the states that have all A on the first component are again the stochastically stable states. Proof uses a pretty standard result in this area that identifies the stochastically stable states in terms of trees of minimum potential. And since I don't have that much time, what I will do is let's say that we have a tree. And a tree is rooted at a node X. And from every other node, we have a path from that node to node X. And the resistance of an edge was defined on the previous slide. And it's 0 for optimal moves. And it's epsilon to some, and it's the power of epsilon for non-optimal moves. So only the non-optimal moves have positive resistance. And I compute the total resistance of a tree. And the tree that has smallest resistance is the one with the minimum, is the one that corresponds to stochastically stable states. Now, I've used this criterion to transform a tree, an arbitrary tree, into a tree with smaller potential for the case of where the state is all A's on the first component. And I won't describe that. The crucial property here is that it is a potential game. And there is a mechanism-like statement that one can recover in the case of potential games with interactions. There is an application to Schelling segregation model, which is, again, close to a potential game in the version that I'm talking about. A one-dimensional case was done by Peyton Young. A two-dimensional model has been considered by Zhang and Policott and Weiss. And I'm going to go over the specific details. It's not directly following from the properties of a potential game. So this result has extra features that are not directly following from that. Finally, maybe I'll jump on the time because my time is out. And one extra complication to the model is the following. Before I was passing activation from one node to another node. In other words, the number of people that got activated was constant for the network. Now I'll have a model called the influence model that was considered in the computer engineering literature, particularly a version called the evil rain model. And the idea is that I have two states, 1 and 0, which inject activation and deactivation in the network. And those activation in the network perform a random walk until they get hit by a deactivation result. And so this is how the evil model works. Again, we can specify this as a Markovian model on the state of the system times the specification of who gets updated or not. And again, stochastic stability is the same as all A states. Coming back to the question that motivated me, I've only done mathematics so far. Can this be done to simulations? I do believe that's true, and there is as I said yesterday in an observation, there is an approach in computer engineering called model checking, which allows you to invalidate certain computer systems. And what I tried here is to come up with a few elements of a language that would be able to specify such social simulations in order to be able to attempt to generalize model checking to those systems. The ingredients would contain context as first-class objects, and based on my discourse representation theory, I think I would like to use situation theory as previously developed, which is the underlying model for the discourse representation theory. The system has to express some form of causality. I know that that's a big one, and I don't mean that you can do everything on a computer. I don't have that pretense. And it has to have, as an ingredient, a way to have processes as first-class objects. It has to be able to quantify, to express properties of processes, to reason about processes, and so forth. And moreover, since logic is going to be used not for inference, but for specification, I want to be able to go from a specification to an executable model, one that I can simulate efficiently, so that my model checking can be done in polynomial time. That is it.